in the part 1 of this webinar series. Now we are going to discuss the remaining part of the PSC box girder bridge. So let me just take you through what all things we have covered up till now in this webinar. So as we discussed earlier, we have considered the modeling of the PSC box girder bridge, which is having a span of about 131 feet and the dimensions as below. And we have already completed the modeling of this particular bridge, the modeling of the geometry, then the modeling of the boundary conditions, as well as the tendons profiles are already created. Now, in this particular part, we shall look into the load definition in Midas Civil Annex. Then we'll try to define the moving load analysis part. Also, once we have defined both the things, we will then try to check the analysis results. And finally, we will look into the design of PSC box girder bridge with the help of Midas Civil Annex. So without further ado, let's go to the model itself. Yeah. So as you could see from the previous definitions, we have created the nodes elements, the material properties and the section properties we have already given. We have also considered 4 support locations and 4 elastic links to define the bearings. We have also considered rigid links to connect the girder with the bearing top. Then we have considered certain tendon properties as per CB FIP, and then we have considered the tendon profiles as well. So with this definitions, now we shall look into the static load definitions. So to define static loads in Midas Civil Annex, we shall go to loads, then static loads. Then herein we can define different static load cases. So currently we are going to define four static load cases: self-weight, crash barrier load, wearing course load, as well as a pre-stress load. So let me just define it one by one. So the name self-weight, then the type as dead load. I'll click on add. Similarly, SIDL wearing course, change it to the type to dead load of the wearing surface. Click on add. Next, SIDL crash barrier, change the type to the dead load of components and attachment. Click on add. And lastly, the pre-stress load case. And let's change the type to pre-stress and click on add. So in this way, we can add the different load cases in Midas Civil. Now, we would like to define the loads for each load case one by one. So let's see how do we define static loads part first, that is the self-weight. So herein you could see the self-weight option. So in the self-weight, we shall select the load case as SW. Then, as we know, Z direction is the vertical direction. So I'll put a scale factor of -1 in the vertical direction to consider the self-weight of the structure. I shall click add. I shall click close. So you see in the tree menu, the self-weight in the Z direction with a -1 scale factor has appeared. Similarly, let us now try to define the wearing course. So the wearing course and the crash barrier loads will be applied as the UDL in this particular bridge. So let us try to define the UDL onto the structure. So we'll go to loads, static loads, and herein you could see beam loads. So in the beam load, we can choose between the different options, element type, line type, or typical type. So currently, as it is an UDL, I would select element type. Let's select the load case to be SIDL wearing course. Then the intensity of the loading is to be specified, that is W. So as this is a wearing course, so depending upon the density of the bitumen that we are using and the thickness of the road, we shall calculate the UDL onto this particular structure. So we have already calculated it, and it is around 1.2 kips per feet. So let us first change the units to kips per feet. Then let's apply the UDL of 1.2 in downward direction, so minus 1.2 kips per feet. Let us select all the elements over which the loading is to be applied. Click on apply. So in this way, the SIDL wearing course is applied. Similarly, now I have to define the crash barrier loading on both the sides. So let us just turn on the hidden view. Let us see it in the side elevation. So I am now going to apply the crash barrier loading on both the sides of the structure. So let us see. Let us change the load case to SIDL crash barrier. Then I am going to define certain eccentricity for this particular load. So the eccentricity in this case is calculated to be about 14.17 feet depending upon the transverse dimension of my girder. So I want to give it an eccentricity with an offset in the global y direction with a distance of 14.17 feet. The intensity of the UDL in this case for the crash barrier is about 0.5 kips per feet. Let us select the elements again. Click on apply. So herein you could see that I have applied a crash barrier loading on one side. Similarly, I shall apply the crash barrier loading on the other side as well. So let us give a negative eccentricity now. Let us reselect all the elements. Let's click on apply. So in this way, the crash barrier loading can be applied onto the structure. Then the next load case is the pre-stress load case. To apply the pre-stress load in Midas Civil NX, you can go to static loads, drop down. In this drop down, you will be able to find the pre-stress loading option. In the pre-stress load, we have different considerations. We have already defined the tendon property. We have already defined 8 tendon profiles in the previous session. Now we are going to define the tendon pre-stress. So you can click on tendon pre-stress. In the tendon pre-stress, we shall select the pre-stress load case. Then we can define different pre-stress values for different tendons. So if you remember, we have defined 8 tendons in total, 4 in one web and 4 in other web. So currently I have calculated the pre-stress value in the tendons to be similar in all tendons. So for all the tendons, the pre-stressing force will be similar. So let me just select all tendons together, and you can push this arrow button to select all the tendons. Next, I would like to give a stress in this tendons, the force option is also available. Let's change the units to KSI. So kips an inch. So the stress which will be acting will be on both the sides. So stressing will be done on both the sides, that is the jacking. Let's apply a pre-stress of 200 kips on both the sides and just click on add. So you see the tendons are highlighted over which the pre-stress is applied. So depending upon the pre-stressing that is done in each tendon, we can define different pre-stress for every tendon. So once we are done with the definitions of the static loads, we can now move on to the definitions of moving load. So for the definitions of moving load in Midas Civil Annex, we can go to moving load option from the drop down itself. Herein you could see that there are different codes which are mentioned. So depending upon the moving load analysis that you want to carry out, we can check on the code that we require. So currently we are going to define the moving load as per ASTO LRFD. So let's click on ASTO LRFD. So you see there are different options which are available as per this code. So there are different options to define traffic lanes in Midas Civil Annex. So one option is to define traffic line lanes and the other option is to define the traffic surface lanes. So the traffic line lanes are used when we are going to do a line modeling, and the traffic surface lanes are used when we are going to do a plate type of a superstructure modeling. So currently, as we have discussed, the model of this particular structure is line type. So we shall define traffic line lanes. Once we have defined the lanes, we can move on to the vehicular definitions. In Midas Civil Annex, we have already the inbuilt data for each code separately, and we could use those vehicle definitions for our analysis. Next, we have this moving load cases in which we can define different moving load cases depending upon the combinations of the vehicles and the lanes that we consider in the moving load analysis. So let's try to see each option separately. So firstly, I shall define traffic line lanes. In Midas, we have option to define the normal traffic line lanes. Also, we can perform the moving load optimization. So the transverse lane optimization as well as the moving load optimization is possible in Midas Civil Annex. Currently, we are going to do a simple moving load analysis and no optimization as of now. So we shall click on traffic line lanes, then click on add. So in this particular definitions for the traffic line lanes, let's try to input the details. So let's name the lane as lane 1. Then the program asks us about the eccentricity of that particular lane. If you go in the top view, you could see from the central line of this particular structure at what eccentricity the lane is to be placed, right? So let's try to place the lane at a certain eccentricity of, let's say, 3 feet from the center line. So it is about 36 inches. So you can calculate the eccentricity depending upon the most critical condition as per your requirement. We are just considering an example eccentricity as of now. Then, once you have defined the eccentricity, the wheel spacing is automatically catered for depending upon the type of vehicles for each code. So currently a 72-inch of wheel spacing is considered here. Then we can also consider the centrifugal force by defining the left wheel of a vehicle which is moving forward. So I have considered the factor of 0.5 as of by default. And as we have already discussed about the transverse lane optimization earlier, the transverse lane optimization option is also available for ASTO LRFD. In that case, the allowable width for the transverse lane uh, can be considered. Then the vehicular load distribution can be done in two ways. First is the lane element type, and second is the crossbeam type. So the difference in between these is the type of the structure we are dealing with. So when we consider the line element type option is used when we are going to consider the structure to be a single line element model as this particular bridge. Similarly, when we are having a grillage type of a model, then we can go for the crossbeam type of approach. So the program in this crossbeam approach can consider the distribution of the moving load, that is the vehicular loads through the crossbeam of the structures on to the main girders. So currently, as we are going to consider the line element type modeling, I have selected an option for line element in the vehicular load distribution. Next, the moving direction. So the vehicular movement can be considered either in the forward, backward, or both the direction. So let's keep it both in this current scenario. Now, let's try to define the traffic lane. So the first point is to be chosen, and similarly the last point. Let's click on apply. So you see in this way we can define the moving load cases lanes, right? So this is the first lane that we have considered with with an eccentricity of about 3 feet from the center line, right? In this way you can define many lanes as per our requirement. Currently we are going to consider only a single lane. So once we have defined a traffic lane, now we can define different kinds of vehicles. So let's click on vehicles and click on add standard. Herein we can define different vehicles as per different codes which are available internally. So we can define it as per LRFD, then standard loads, and many other load cases, load codes, moving load codes to be considered. Currently, let's keep it as ASTO LRFD type of load. Herein, we are getting different types of vehicular definitions: HL93 truck, HL93 tandem, and even the HS20 fatigue vehicle. So, depending upon the type of the structure we are dealing with, we can choose the vehicle. So, let's say for now, I'm going to consider HL93 truck. Then you could see that the loading for this particular truck is already considered by the program automatically. So these are the predefined in the database and we can use them directly. So herein it is an option to consider whether you have to consider centrifugal force as well. Currently, as the bridge is straight, the centrifugal force won't come into picture. So we can ignore that for now. So once we have selected the vehicle, we can click on apply. We can also add another vehicle, let's say HL93 tandem type of loading, and just click on apply. So we can add different types of vehicle as per our requirement. If any type of a vehicle which is not defined in this particular standard database, we can always use the add user defined vehicular option, in which we can define different trucks, legal or permit loads, then the train and the permit truck loads. So the user defined vehicle can also be used. So once we have defined the lanes and the vehicles, now we can create different moving load cases. So let's click on moving load cases. Let's click on add. So let's give the load case name as moving load case 1. You see here the load case for permit, whether this is the load case for the permit vehicle, we can check on if we are going to consider the permit vehicle, but currently no. Moving load optimization, whether this particular load case is to be considered for the moving load optimization, we can consider that as well. Herein, certain additional information corresponding to the number of lanes and the loaded lanes is to be considered in that case. Similarly, if we have multiple lanes, then the multiple presence factor for different number of lanes has to be considered, right? So the program will automatically take care of that internally. So the scale factor as per ASTO LRFDs for number of loaded lanes to be 1 is 1.2, for 2 is 1, and so on. So depending upon that number of loaded lanes that the programs considered in the analysis, the multiple presence factor is automatically considered. Then we can choose whether each subload case that we are going to define further shall be acting in a combined manner or an independent manner. So let's add a subload case. Click on add. Select the vehicle which we have already defined. Then we can add a scale factor to the vehicular load. Also, there is an option to consider the minimum number of loaded lanes and maximum number of loaded lanes. Currently, as there is only a single lane being defined, the minimum could be 0 and maximum could be 1. So let's select the lane over which the HL93 truck is to be loaded and click on OK. Similarly, we can add as many as load cases as required, and the effect could be combined or independent. So let's add a tandem truck as a tandem vehicle as well. So once you define the moving load case definitions, just click on OK and the moving load case shall be added. Let's click on close. So in this way, the different moving load cases can be defined in Midas Civil NX. So this is the preliminary definitions of different loads which can be applied on a bridge. Certain simpler examples are considered here. Now we shall see the analysis of this particular bridge that we have modeled, and we shall see the results. So for analysis, we shall go to the analysis tab. Then we can define different analysis criteria for each analysis separately. So we can define the moving load analysis criteria. So let's click on that. So herein we can use different options to control the analysis type, to define how many iterations are to be done, what are the points, influence generating points are to be considered. So what is an influence generating point is basically in Midas Civil NX, we consider the moving loads to be applied depending upon the influence line diagram approach. So influence line diagrams are used to finalize the position of the vehicle in to consider the maximum effect for the loading, for the reactions, as well as deformations. So currently the program asks whether how many number of points that are to be considered for each element for the influence generation. So depending upon the accuracy of the analysis which is required, we can change those. Currently, I shall keep it as by default. Similarly, in the other options, as you could see below, we can define the analysis output results that we require. So I'll just click on OK and keep it as by default. So if you're trying to model any other type of analysis, then we can consider different analysis controls such as the P delta analysis, the buckling analysis, eigenvalue analysis, heat of hydration analysis, etc. Similarly, there is settlement analysis, nonlinear as well as the construction stage analysis. So we can consider these type of analysis and define the analysis control for them in Midas Civil. So currently, as we are only considering the moving load analysis differently, so we shall only define the moving load analysis control. So once we have defined all the analysis control types, let's perform analysis for now. So click on perform analysis. And you could see that the analysis has been performed successfully. In the message window, it is visible. So you see your Midas job successfully completed. So in this way, the analysis can be considered. Now, once we have carried out the analysis, let's try to verify different results, outputs that we can get from Midas Civil NX. Herein, we can get different outputs depending upon the type of the bridge that we are considering and the type of analysis that we are doing. Currently, we are only considering the analysis results as per the defined. We also can see the analysis results for the time history as well as for different specified bridge such as the cable state bridge separately as well as the heat of hydration analysis, right? For now, currently as we are going to consider the static and the moving load analysis, let us see how we can see the reactions first. So just click on reactions and the reactions forces last moments can be seen. So firstly we shall choose the moving load, so firstly we shall choose a static load case such as sulfate and we shall see the reaction in x, y and z direction. Turn on the values, turn on the legends, click on apply. So herein you could see that the reactions which are generated in this particular girder are about 425.7 kips on both the sides at each node, support node. So this can also be seen with respect to the SIDL varying course. So now we can consider the reactions in all the directions, and if you turn on the legends we can see the results in this tabular window as well. Next we shall verify the deformation coming onto this particular structure. So click on deformations, deformed shape. Let's see the deformation under the sulfate. So let us see from the side view. So you could see that the maximum deformation in this particular structure is about 0.8 inches. Now let us see the deformation under the pre-stress. So the pre-stress which we have applied is considering a deformation of 0.756 maximum in the center. Similarly, we can verify the results for different forces inside this particular structure. So click on forces. Herein we have different options to check the forces. Let us see the beam diagrams. So the beam diagram for the self-weight load case in terms of the bending moment My is shown here. So we could see that the maximum sagging moment of around 2.82 into 10 power 4 kips feet is shown here in the diagram. So the bending moment diagram is quite similar to the simply supported beam bending moment diagram in case of self weight. So we can also verify the shear coming onto the structure and other entities such as the transverse bending moment as well as the transverse shear as well as the axial force. So we could see that under the self-weight load case, a certain axial force is being generated in the structure. So in the pre-stress load case, a maximum axial force of 5.85 into 10 power 3 kips is generated. Now, in this way, we can see the results for the forces which are generated into the structure. Now, if you want to copy or if you want to verify the results in the tabular format, we shall click on this particular three dots and see the results for each load case separately in the tabular format. So these tables are Excel compatible and can be copied and considered for the verification in Excel as well. So once we have done with the forces, let us see how do we see the stresses in the structure. So click on stresses. So we can click on beam stress diagrams for these particular box girder bridges. Let us select the self-weight load case again. Herein we can verify different stress results. So SAX corresponds to the axial stress, SSY, SSZ corresponds to the shear stress, SBY and SBZ corresponds to the flexural stress, and we can also consider the combined stress option. The combined stress can be considered. So in this diagram, we can see that the stresses at different locations can be verified. So 1 2 corresponds to the topmost location and 3 and 4 corresponds to the bottom location of that particular girder. To the extreme flanges point at the top, and position 3 and 4 are the extreme bottom flange points at the bottom. So I want to see the results at the bottom of my girder. So let's select position 4 and click on apply. So we could see that around 0.8 kips per inch square stress is generated in this particular structure under the self-weight load case, and it is in tension right now. So positive is tension. Let us see the results for the top location, that is location number 1, and click on apply. So a compression or a compressive stress of about 6.674 ksi is seen in this particular case. Let us also verify the stresses under the pre-stress. So under the pre-stressing force, we can see both compressive as well as tensile force in the structure at the top of the girder. So this is basically due to the type of the profile that we have considered. Similarly, at the bottom, we could see that a compressive stress is generated due to the bending of this particular girder under the pre-stressed load case. So in this way, we can verify different stress coming onto the structure under different load cases. Now, if we also want to consider the verification of stresses under different load combinations, we can define the load combinations first here. We shall go to concrete design. Herein, there are two options to generate or to verify the load combinations. We can input the load combinations from the Excel directly, or we can type here. And also there is this auto generation feature which is available here to generate the load combinations automatically. For that, we shall consider the design code. Once we consider design code, we can define the load factors that are to be applied. So let us consider both. Then for these are the advanced option for the seismic load combination as well as the settlement analysis, etc. So once we have defined those load cases as well, we can use these options too. Currently, let's click on OK to generate the load combinations as per AASHTO LRFD 2020. So you could see that different load combination in terms of strength as well as serviceability are generated by the program for us. Let's close this. Now, let's say I want to verify the results of the load combination number 12. Click on apply. So these are the stresses which are obtained in the load combination number 12. You can see the stresses in the serviceability checks or serviceability load combinations also and verify the stress checks here. Once we have done that, we can also see the results for the moving load analysis. So for that, let us see the reaction or the maximum reaction which is generated as per the moving load case that we have defined. For that, let's go to MV max and MV min. So MV max and MV min are basically the maximum and the minimum reactions which are generated at that particular support with respect to the moving load case that we have defined. So the maximum reaction under the moving load is found to be around 92 kips. Similarly, the minimum reaction is 0. So in this way, we can see the results for the moving load analysis as well. So let's verify the results for the bending under the moving load case. So this is the maximum bending moment which we are getting under the moving load cases as well. Also, there is this feature of moving load tracer wherein we can see the vehicular position for getting the maximum bending moment, maximum reaction or maximum displacement. So let's verify the results for the position of the vehicle for maximum bending moment in the structure at the center. For that, let us select the element somewhere at the center. So element number 22. You can select the location at which you want to see the results. Let's click on apply. So you could see that here is the moving load tracer option and it has generated the position of the vehicle for which the maximum bending moment of about 4 point, yeah, about 4000 kips feet is generated at the center of this particular girder. So this shall be the position of the vehicle for which this maximum moment at the center is generated. So this is very useful when we are dealing with the high span or the long span bridges, so that we can manually verify the location of the moving loads for the maximum results. So in this way, different results can be verified in Midas Civil. So once we are done with the results, now we shall go to the design feature in Civil NX. So let's click on design. So you could see that we can define the design as per PSC. So let's click on PSC design, and herein we can select the different codes as per requirement. So ASTO LRFD 20 is selected for now. Then we shall go to the design code option. Herein different criterias are to be considered. So the tendon type can be considered, the class or the exposure for the crackwood checks can be considered. Similarly, other conditions which are used in the design of a structure are given, and those can be verified in this case. Now you are also consider the output parameters herein. So we can define the output parameters which are required for the design. So let's select all for now and click on OK. Next, in the design parameters, we can select the different PSC segment assignments as per our requirement and serviceability load combinations type. So if we are auto generating the load combinations, the program will automatically segregate the serviceability load combinations into service limit 1 and service limit 3. Then we shall modify the material type for design. So C5000 was considered. Let us try to define the rebar data for the design. We shall select ASTM 19RC and select the main rebar grade. Click on modify and click on close. Then we shall specify the design position for which the design is to be carried out. So let us select element number 22, which is the center of our structure, and click on apply. Similarly, we can define the design position for output, that is generating the reports and the results. Again, we can select element number 22 and click on apply. We can see that the element number 22 is selected for the result output definitions. So once we are ready with the design options, we can perform design. But before that, we can also specify the reinforcement into this particular structure. So before performing, let us try to define the reinforcement in the girder section. For that, we shall go to properties. Therein, we can go to section manager and click on reinforcement. We shall select the required section and try to define the reinforcement. Let us select the input method 2 and try to define the starting and the endpoint for my reinforcement. Let us say I am willing to have a center to center spacing of about 1 feet in between the reinforcements, and I am going to consider the reinforcement to be end to end. Let's say the diameter of the reinforcement is 5 grit bar Click on add. So in this way, the reinforcement can be defined. Click on apply and click on close. Now, as we have defined the reinforcement, let us try to rerun the analysis, and now we can design our structure. So for designing, we shall click on perform design option, and the design is done. So let us see how we can verify the design results. Firstly, we can see the design forces which are coming onto that particular structure. So let's say for the element number 22, I want to see the design forces. So these are the design forces which are coming under each load case separately. If I want to see the results for the flexural strength of my girder, click on check flexural strength. Herein we can see that for the element number 22, certain positive moment is generated under the load combination number 13, and all the parameters related to the MUY, MCR, MNY and phi MNY etc. are generated by the program, and the ratio of the demand to the capacity is coming out to be around 0.34. So in this way, the results could be verified. Similarly, the results could be verified for the shear strength, for combined flexural and shear and torsion, and also the different stress results can be verified. So once we are completed with the design part, we can check the results under different criterias. We can also generate the results as per the PSC result diagrams. So click on PSC result diagram. If I want to see the design results for flexure, I have selected flexural Y. Click on apply. So we could see that for the element number 22 that we have considered for design, the capacity of this particular structure is higher than the demand in this particular structure. Right? So this diagrammatic representation of capacity and demand in case of flexure is shown here. Similarly, we can consider other parameters such as shear, torsion, etc. to consider the design of that particular structure, results for the design of that particular structure diagrammatically. Finally, we can also generate an Excel report. So click on Excel report, and the program shall generate an detailed design Excel report for us. So we could see that an Excel report is generated by the program. So for the element number 22, all the data related to the material definitions, etc. is given in this sheet. For the flexural design checks, the flexural moment is calculated and the flexural resistance is calculated. Similarly, the minimum reinforcement checks as well as the moment in negative direction is also considered. The shear design checks are considered by the program and a detailed design report is generated. We can verify this particular detailed design report as per our requirements and iterate the solution as per the requirement. Similarly, we can see the tabular format for the different results. So stress results, the principal stress results, the tendon stress results, etc. can be verified from this particular sheet. So in this way, the complete design of the PSC box girder bridge can be done in Midas Civil NX. I hope that the session was informative. I thank you everyone for joining this session. We hope that